Two pure tones with the same intensity but different frequencies sound different, and two sounds with different frequencies and sound pressure levels may sound the same. It can be seen that doubling the intensity of the sound does not equal doubling the loudness. The relationship between subjective feelings and objective physical quantities is not a simple linear relationship. Therefore, 1000 Hz pure tone is used as standard sound. The sound pressure level of the pure sound that is as loud as the sound to be measured is defined as the loudness level of the sound to be measured. A pure tone is a simple harmonic signal of a single frequency. The unit of loudness level is Fang. Points on the same pure tone equal loudness curve have equal loudness levels. For example, the loudness level of a 1000 Hz pure tone with a sound pressure level of 50 dB and a 50 Hz pure tone with a sound pressure level of 72 dB is 50 Fang, with sounds the same. As can be seen from the figure, the curve from 2000 to 5000 Hz is flat, indicating that the human ear is sensitive to the sound in this frequency range. The human ear is less sensitive to low frequency sounds. The curve with a loudness level of 0 at the bottom of the figure is the audible threshold, indicating the limit where the human ear can just hear the sound. The uppermost curve with a loudness level of 120 is the pain threshold, which represents the limit at which the sound can make people feel pain. These two curves contain the range of sound pressure levels that the human ear can perceive. The compound sound cannot directly adopt the equal loudness curve of the pure tone, and the loudness level needs to be obtained by calculation. The loudness level measuring instrument is a sound level meter. There are 3 weighting networks ABC in general sound level meters, and 4 weighting networks ABCD in a few sound level meters. Network A refers to the 40 Fang equal loudness curve, which has a greater attenuation of the sound below 500 Hz, simulating the insensitivity of the human ear to low frequencies. The network C line is relatively flat, and it hardly attenuates in the entire audible range. It simulates the response of the human ear to pure tones above 85 Fang and can represent the total sound pressure level. Network B is between the two, with a certain attenuation of low frequencies, simulating the response of the human ear to a 70 Fang pure tone. Usually, the human ear's perception characteristics of less strong sounds are close to the equal loudness curve of 40 Fang. Therefore, network A is actually used more. For composite sound, not only need to know the total sound level, but also need to analyze the frequency components, such as noise. It is necessary to find out the prominent frequencies to eliminate in order to effectively reduce the noise. The composite sound was analyzed using a spectrogram. The upper image is a linear spectrum, and the lower image is a continuous spectrum. Spectrum refers to the combined amount of sound pressure levels at various frequencies. The spectrogram takes the frequency as the abscissa and the sound pressure level as the alternate. The lowest frequency is called the fundamental frequency, such as 440 Hz in the figure above and 31.5 Hz in the figure below, and the harmonic frequency is an integer multiple of the fundamental frequency. The bandwidth of the frequency band can be narrow when the accuracy is high, and can be relaxed when simple measurement is allowed. The frequency bands are divided according to the number of frequency bands of its frequency band being equal. N is equal to the base 2, logarithm of the ratio of the upper bound frequency and the lower bound frequency, which is a positive integer of fraction. Using the logarithmic score of the frequency coordinate axis to represent the center frequency of its frequency band, it can be divided into equal distance. N equal to 1 is called octave, which is used for general engineering measurement. The following figure is an octave spectrum. N equal to 1/3 is called 1/3 octave. and is used for high precision laboratory measurements. Directivity is a characteristic index that describes the intensity distribution of salt radiated by a salt source in a free salt field. When the size of the salt source is much smaller than the wavelength, it can be regarded as a non-directional point salt source, and the salt pressure level at the same distance from the center of the salt source is equal. When the size of the salt source is similar to or larger than the wavelength, the salt source can be regarded as composed of many point salt sources. The superposition of the salt waves radiated by these point salt sources will result in different radiation in all directions. The salt pressure levels are no longer equal for spatial locations in different directions equidistant from the center of the salt source. The greater the size of the salt source than the wavelength, the stronger the directivity. The directivity of the salt source is usually represented by a polar plot. Points on the same curve have equal salt pressure levels. As can be seen from the figure, the higher the frequency, the stronger the directivity. Direct salt energy is concentrated near the radiation axis of the salt source. There are two main ways to express the salt source directivity. One is the directivity index, taking the salt pressure field formed by a non-directional point salt source with the same salt par as the reference value. The difference between the actual salt pressure level and the reference salt pressure level in a certain direction at the same distance from the actual salt source is called the directivity index of this point, also in decibel. The distribution of Di is generally obtained through field measurements. The second is the directivity factor, defined as the ratio of the actual salt intensity to the salt intensity of the above reference salt field. The relationship between the two indicators is the directivity index is equal to 10 times the base 10 logarithm of the directivity factor. Human subjective auditory characteristics may include audible frequency limit, audible salt pressure level limit, minimum intelligible threshold, haze effect, masking effect, and auditory localization. Different people have different audible frequency limits. The highest audible limit is related to the loudness level, and the lower limit of the lowest audible frequency is usually 20 Hz. As the age increases, the lower limit of audible frequency continues to increase, and middle-aged and elderly people become less sensitive to low-frequency sounds. The range of loudness that can be received by the human ear varies greatly, and an increase in the minimum audible limit means a decrease in hearing sensitivity. The upper limit of the tolerable salt pressure level is related to its noise exposure experience. Different people have different minimum intelligibility thresholds for different frequencies. The haze effect reflects the auditory persistence and salt emits localization of the auditory characteristics of the human ear. The reflected sound arriving within 15 milliseconds of the direct sound will strengthen the direct sound, and the reflected sound arriving after 50 milliseconds will generate an echo. The sound direction is determined by the closest sound source, not by the sound pressure level. Since the direct sound of the single sound source arrives first, the direction of the sound source heard is the same as that of the sound source. When there are multiple sound sources, the sound emits localization problem needs to be considered. Masking effect refers to the phenomena that the human ear's hearing sensitivity to one sound is reduced due to the presence of another sound. When one sound is 10 dB higher than the other sound, the masking effect of a sound with a small sound pressure level on a sound with a large sound pressure level is very small and can be ignored. The characteristics of masking are: the sound with close frequencies has a significant masking effect. The higher the sound pressure level of the masking sound, the stronger the masking effect. The low frequency sound has a greater masking effect on the high-frequency sound, while the high-frequency sound has a limited masking effect on the low-frequency sound. Auditory localization means that the human ear can judge the direction and distance of the sound source. Width is determined by the time difference and the intensity difference. When the sound waves emitted by the same sound source reach the two ears of the person, the human ear has poor accuracy in determining the distance of the sound source and is very accurate in determining the direction. Usually above 1400 Hz, mainly depends on the intensity difference. Below 1400 Hz, mainly depends on the time difference. The human ear can distinguish the orientation of the sound source better in the horizontal direction than in the vertical direction. Think about it. How to arrange speakers in a home that relies on electroacoustics to ensure that people can judge that the sound and the image are in the same place? How does architectural design take advantage of the masking effect?